Okay, good morning, everybody. This talk is beyond ByteBuffers. I am not Maurizio Cimadamore. Unfortunately, Maurizio is taken ill, and so you get me instead. Sorry. By way of lowering expectations, I just saw these slides for the first time, like last night. So it may not be as smooth a presentation as you're expecting, but I will try to get the information across. So what do we mean by beyond ByteBuffers? So the ByteBuffer API was introduced in Java 1.4 primarily for non-blocking I/O, but it gets used a lot for accessing off-heap memory. And as we'll see in, later in the slides, it's not exactly the ideal tool for that, but we use it for that anyway because it's what we've got. And this talk is about work that came out of Project Panama. Project Panama is about better interop between Java and native code, C code. And not surprisingly, in the course of addressing the issues of better interop with native code, we had to address better interop with the native heap. And as often happens, part of a project sort of can be distilled out and delivered separately because it's more generally useful, not just to the project that it came from, and this work fits into that category. So I'm going to be talking about a new API for off-heap memory access that hopefully will replace ByteBuffer, or hopefully you're not using Unsafe for that. So let's get started. This is how you know I work at Oracle. And let's talk about off-heap, okay? So Java applications sometimes want to access memory that is not in the Java heap, the managed garbage collected heap. And this could happen for a number of reasons. You just don't want to deal with garbage collection. You want to do your own memory management. You have to share data with native libraries or share data across multiple processes, and you want to use shared memory for that. Or maybe your application is just a big cache, like a memcached kind of application, and you're just going to serialize data right into some big, big buffer, and that's all you needed to do. And so what most people use for this is the ByteBuffer API. There are other alternatives that are generally worse. Some people use Unsafe for this. We would like to continue to make Unsafe recede in importance and eventually go away. So we're not encouraging people to use Unsafe for this. But the deal that we've made about taking away things that are part of Unsafe is, well, we have to provide you a safe performance-supported alternative before we do that. So, the API that I'm going to talk about today, is a candidate for that. So, first, let's talk about the ByteBuffer API. How many people here have programmed with the ByteBuffer API? Okay, so good. That's most of you have. So I'm going to do a quick overview of what ByteBuffers are. Like I said, they were added in Java SE 1.4, and they were added for purposes of doing non-blocking I/O. So a ByteBuffer is it's a region of memory that can that you can put data into, take data out of, and it's a stateful thing that you pass around. So if you want to read from a socket, you in a non-blocking way, you pass a ByteBuffer to the socket API, and it's going to fill it up with some data. And then, when you get the buffer back, you can inspect it to see how much data was put into it. You can take data out of it, and it was designed around the use case of you don't necessarily know how much data your counterparty is going to put into the buffer. And so there's a protocol for switching between I'm filling up the buffer, I'm taking data out of the buffer, and handing it back and forth. One of the challenges of this API, especially for use in off-heap application, is that it's quite stateful. There's a number of aspects of state in the buffer of where is the next point I'm writing to or reading from, how much of the buffer have I written, when I read from it, I'm going to have to update one of these pointers. When I write to it, I'm going to have to update one of these pointers. And having all of this state makes it harder for the JIT to optimize and inline through. So, the ByteBuffers are a pretty good match for the asynchronous I/O, the non-blocking I/O use case that they were invented for. They're a little bit less of a good match for off-heap. So quick example of how ByteBuffers work. So here I'm going to be reading from a channel. So I get a file channel. I allocate a ByteBuffer of length 10. And then I'm going to read into that ByteBuffer. And then I call this method flip, which is switch from reading mode into writing mode, right? So the I've passed the buffer to the to the read method. It may or may not put any data in the buffer, and now I want to get the data out that it put in. So I flip into reading mode and loop through the elements of the buffer until I'm done. And at the end, I say clear, which means reset the buffer to its initial state. And so the way that works is my buffer is 10 characters long. Initially, its initial writing position is at the beginning. Its limit is at the end. And then I read from it, and it's going to put some characters in. So now it's moved the position forward, which indicates here is the next place I would add something to the buffer. And then when I call flip, it flips the pointers around where the position is, instead of being the next place to read, it becomes the next place to read from. So next from right to read. I got that backwards. Okay, and then I loop through saying, get me a byte, and that has the effect of moving the position forward each time I read a byte. And eventually, when I've read all the bytes, I get to the end, I clear it, and it resets the pointers. It doesn't erase the data. The data is still in the buffer, but it just resets the pointers. Okay, so this is the basic dance, that you're always doing with ByteBuffers, where one activity is filling it up, another activity is draining the buffer, and when you switch between those modes, you flip. Okay, fairly straightforward. So, like I said, this was added to support asynchronous I/O or non-blocking I/O. And works great for that use case. But if you want to interact, say, with native code, where you're going to have some native activity that's going to fill up the byte buffer, or you're going to share data between multiple processes, you don't want the thing moving around on you. You would like to have the buffer be in a stable location rather than just backed by an arbitrary byte array in the managed garbage collected heap. There's a bunch of ways to do that. We could have done that by giving you a way to say, pin the thing in memory. So ask the garbage collector not to move it. Pinning objects has other consequences for garbage collection that aren't always good. What was invented at that point was this notion of a direct byte buffer, which is backed not by an array in the managed Java heap, but in the native heap. So we call that off-heap. It's not really off-heap. It's off the Java heap. It's on the C heap. So a direct byte buffer is backed by a non-moving buffer in the unmanaged C heap. Okay, so the only difference in the example, if I wanted to use direct byte buffers, instead of saying byte buffer allocate, I would say allocate direct. And that says, instead of giving me basically a new byte array, it goes off to the C heap and does a malloc. So people like this. It's a useful tool. And a lot of people said, hey, this was kind of meant for non-blocking socket reads or, character encoding, decoding, and things like that. But I could use this just to allocate myself, a big region of memory that I'm going to manage myself and get reasonably fast access to it. And it's safe because access to it is bounds checked. So if you try to read outside the bounds of your buffer, you'll get an error. And it integrates nicely with garbage collection in that when the buffer goes out of scope, everything gets deallocated. So that feels like it would be a good match for off-heap access, and a lot of people have used it for that. But it's not a perfect match. So let's take a look at what the performance looks like. Like I said, it's bounds checked. That means every time you read or write, there's some kind of comparison of are you trying to read beyond the boundary, or you're trying to write beyond the boundary. So we took as our baseline for our this set of benchmarks unsafe on the theory that that's basically gets translated directly to memory access instructions, and so we have a little benchmark that loops through a buffer and just reads all the bytes out and adds them up. And so the throughput, we got a certain throughput of that, and let's compare that to doing a similar thing with ByteBuffers. So here's the equivalent program with a direct byte buffer. We've allocated a byte buffer, and then we loop through saying, do you have more data? If so, get me that int value, and we'll add them up. And what we see is the throughput is considerably worse, factor of 6 worse. So that's not so encouraging. Let's see what else we can do to speed this up. It turns out we were interacting with ByteBuffers in sort of the slowest mode possible, where we were like asking, do you have another byte? Okay, give it to me. Do you have another byte? Okay, give it to me. There's also an absolute addressing mode where you can say, hey, I know what's in this buffer. Just go ahead and give me the bytes that are at a certain offset. And that turns out to be, well, a bit faster than the other version. We get about 43 versus 29 on the throughput score. And there are a few things we can do to improve that as well. Turns out that ByteBuffers operate always in big endian mode, which is wrong for most modern systems. And so you can tell it explicitly, I'd rather use the native byte order instead of big endian, and we get a little bit of an improvement out of that. So we're still pretty far away from unsafe, though. We're still about a factor of 4 away. And so that kind of gives us a hint that there is room for improvement. And so why is it that ByteBuffers aren't ideal for off-heap access? Well, they weren't designed for it, right? They were designed for asynchronous I/O access, and they work really well for that. But there are conditions for how they were intended to be used. So, for example, one of the things that's slow, I didn't show benchmarks for this, but relatively slow with ByteBuffers is allocation. If you have allocation-intensive activities, it's not very good. But if you're reading from if you're reading repeatedly from a socket, chances are you allocated the buffer once, and you're going to reuse it over a lot of reads and writes. So that's not much of a problem in that use case. And similarly, most of the time when you're filling up a buffer, well, that data is coming from I/O. And so the cost of the I/O typically dominates other costs like the bounds check. And so all of the housekeeping associated with ByteBuffers generally isn't an impediment when it's used in its intended mode. But when you try to use it as a general off-heap API, the limitations start to show up. So as I said, allocation is expensive, so allocation-intensive applications are going to suffer. The biggest challenge people have with ByteBuffers is they're indexed by ints, and that means we have a 2 gigabyte limitation for their size, which probably seemed really big in the Java 1.4 days, right? Who's going to need more than 2 gigabytes? But one of the most commonly requested improvements for ByteBuffers is, can we have long indexed ByteBuffers? And it sounds like a simple request, but it's not. It would be a fairly invasive change, and that's why we haven't done it. And similarly, the API for ByteBuffers are designed for sequential access, or you can do like your own address computation, and you're on the hook for getting it right. But it's not an ideal match for off-heap. So our theory is the time has come to have an API that's designed for off-heap access, that's fast, that's safe, and that doesn't rely on unsafe. Another thing people complain about when using ByteBuffers in this mode is the deterministic deallocation. ByteBuffers are garbage collected, which is great for safety. Because that the underlying buffer will be deallocated at some point after you're done using it. But if you're allocating fairly large buffers, you might want them to be deallocated faster than that. You'd like to be able to say, close the thing, and know that the resources have been released, and ByteBuffer doesn't really give you that. So here is a sampling of open RFEs against the ByteBuffer API. There's no shortage of things that people would like us to improve about ByteBuffers. And individually, each of these seems kind of reasonable. This is just page 1. But in the aggregate, it kind of paints a picture of, gee, there would be a lot of effort required to take this API and turn it into what people seem to want it to be. So again, that's kind of a hint that we're trying to pound a square peg into a round hole, and with a big enough hammer, you can probably get away with that. But maybe it's better to stand back, think about the problem, and offer up potentially a better solution. Okay, so I'm going to talk about the memory access API. This is something that we are proposing will go in as an incubating module, maybe 14, maybe 15. We're not quite sure yet, but it's approached the point where it's in pretty good shape. It's been used to port several significant projects. So there's real work behind this. This is not just all theoretical hand-waving and such. And like I said, this came out of Project Panama as that was originally needed for something to enable native function calls to work, right? Because if you're calling a native function, at some point it's probably going to hand you back a struct that has pointers in it. And you would like to be able to dereference those pointers. So good interop with native code also means good interop with native data and with a native heap. Okay, so the memory access API, the goal is safe and efficient memory access. And we want it to work in all the modes that people like to use it. You should be able to access on-heap memory that's backed by just an ordinary byte array, and off-heap memory that's off in the C heap. And by safe, what we mean is no VM crashes. You shouldn't be able to dereference the wrong pointer and have that cause a seg fault. So ideally, we would like it to be not only more efficient than ByteBuffer, but more attractive to use so that people will be happy to migrate to it. There are a couple of abstractions in this API. I'm going to talk about them individually, but they're pretty straightforward. The basic one is a memory segment. That's just a block of memory. So a memory segment describes a block of memory, and a memory segment has spatial bounds, which is to say it has a start and an end in memory, and we want to prevent you from accessing memory that's outside those bounds. And it also has temporal bounds, which is to say at some point in time I allocate it and it becomes usable, and then at some other later point in time I close it and it should be unusable after that. And if I try to access it outside of those spatial or temporal bounds, I should get an exception. A memory address is just an offset, within a memory segment. So you can think of that as a pointer. And a memory layout is a description of a data structure laid out in memory. It's like a struct. I'll go through each of these individually. And the other thing that this connects to, we lean very heavily on an existing API that's in the JDK, was added in the JDK in Java 9, which is var handles. Has anybody used var handles? Does anybody know what var handles are? Does anyone know what method handles are? Okay, good. All right. So I will back up and describe var handles a little bit. You've all used reflection, right? Everyone's used reflection, right? So you can think of method handles as being better reflection, faster reflection. Reflection has a lot of safety checks built into it, accessibility checks and things like that. And so it's convenient to use, but it's slow. Method handle is much more of a low-level direct linkage to a method, and it gets used. It's not something that's generally intended to be used directly by programmers. It's used by compiler writers and frameworks and code generators and such. And we use it, for example, in the implementation of lambdas. That we use invoke dynamic to link lambdas, and that involves building method handles to describe what am I supposed to do when I call this and when I invoke this lambda. So if method handles are analogous to the Java lang reflect method object, var handles are analogous to the Java lang reflect field object. They are an abstraction for describing a variable in memory. And it's not just an encapsulated pointer because it can have some context. So you can have a var handle for an instance field, and you can read and write that instance field, but you have to give it something. You have to say, what object am I reading or writing the field from? So, and similarly, you can have a var handle for array elements, but you have to give it two things. When you want to read or write from an array, you have to say, what's the base of the array, and what index am I reading and writing from? So it's an abstraction for describing a variable, which may be parameterized by, what object am I finding this in, or what array am I finding this in, or what offset am I finding it at. And it's a very flexible mechanism, and so we pressed it into service for this, and it turns out to be quite a good fit. All right, so let's do a few examples. So imagine I want to lay out the equivalent of a simple struct in memory. This struct is a point. It's the only example we know, right? Everything XY points is like the only code we get to write as architects. So this is the C version of the XY point. I'll be doing the Java version in my other talk later about Java language futures. And I have an array of these things. So there's 5 points. So that's going to be 40 bytes long. And they're laid out in memory packed XY, XY, XY. OK, great. So there are, if I have a memory segment that describes this, this region of memory, there are some things I might want to be able to do with that. I want to be able to say, well, I want to read the data at a certain offset within the within this segment. And there's an operation for that where I can say, give me the memory address associated with this segment with this offset. Similarly, I might want to say, well, I've got this big segment. It's an array of 5 points. I want to focus on a slice of that array. So take the big segment and give me a new segment that describes a slice of the bigger segment. And because we want to have spatial and temporal bounds checking, if I hand someone that new reduced segment, they can only access the the middle bytes out of it. If they try to back up from it or move forward past it, the bounds checking will catch them and say that's out of bounds, even though it's it's coming from a bigger segment. So these are sort of basic operations on segments and memory addresses that such an API would need to support. The more complicated part is how it accesses the memory at all, which is, like I said, done through var handles. So when we did var handles in Java 9, there were 3 kinds of var handles. There was one for static fields, one for instance fields, and one for array elements. And we're adding a new kind, which is for off-heap memory access. And just as if I want to access an instance field, I have to pass, well, what's the receiver object? What object am I getting the field out of to the var handle in order to do a get or a put? For a memory access var handle, I have to pass it a memory address. So we call those coordinates. A var handle is associated with a set of coordinates, and all of these memory access var handles will have at least a coordinate for a memory address. Some of them will have additional coordinates, which I'll go through in the examples. And then we have API for taking one of these things and deriving another var handle at a different offset, or striding through an array so we can mimic array access. So let's take that same example where we had an array of point structs. We had 5 points. They're laid out X and Y, and I'll show you what the code looks like using the memory access API to access this. So the first thing it does here is says, get me a memory access var handle for an int. And so you should be thinking, okay, what int? Right? How am I going to know what int to read? Well, the way I know what int to read is I'm going to pass you a memory address. So you can think of this as being like a function that takes a memory address and returns an int, or it can take a memory address and an int and write the int to that. So var handles are like fields, so you can use them to both read and write from memory. So far, this var handle doesn't do very much. I can use that to derive another var handle where I say, okay, you have a memory access var handle. Give me a new memory access var handle, but at an offset of 4 bytes. So I'm going to pass you in a memory address, and you're going to add this offset to it and then dereference the address I passed in plus this offset, right? So the first one, if I passed it the memory address of the base of the segment, I would read that first X. And on the second one, I pass in the memory address of the base of the segment, and it would read me that first Y. Does this make sense to everybody so far? A little fuzzy, maybe? All right, let's keep going. Now, I don't want to just access the first element of the array. That wouldn't be very interesting. So I want to be able to say, let's parameterize this var handle so I can pass it not only a memory address but an index, and I can read the first X, the second X, the third X, etc. And so I've taken the Y var handle, and I said, give me a new var handle using the with stride method. which says, take the, I'm going to pass you a memory address and an index, take the index, multiply it by 8, and read or write the data at that offset. And so now here's something where I pass it the base of the offset, base of the segment, I pass it an index, and I can read any of those y values out, y0, y1, y2, etc., just by passing the appropriate index 0, 1, 2. Okay, so with a few different slicing and dicing operations, I can describe offsets within a struct, and I can describe access to array-like data structures, which is convenient because if I'm writing if I'm writing an application that is accessing memory off heap, there's a good chance that the data that I'm accessing has some structured form. It's going to be a big struct or a big array or an array of structs or something like that. And I'd like not to be in the business of computing all of those addresses, right? We like to have the compiler compute addresses for us. When we index into an array of longs, we don't have to multiply by 8. The VM does that for you. You say, give me the third element, and it multiplies that by 8 before it goes and reads and writes from the memory. Okay, so I talked about spatial safety, that you don't want people to be able to read outside the bounds. There's also temporal safety that we have to be aware of. So what temporal safety means, after I close the segment, I've probably deallocated it, you shouldn't be reading or writing that memory anymore. And so not only do we want the resources to be released in a timely basis when we close a memory segment, but we also want to make sure that if someone tries to access a segment that's already closed, then they get an appropriate exception rather than just scribbling over memory that now may be used by something else. With ByteBuffers, we engaged garbage collection to do our cleanup for us, which was reliable, but we didn't always know when it was going to happen. It was reliable but unpredictable. When you have to close a segment yourself, you get predictability, but the responsibility is on you to actually close it. And if you forget to close it, well, that's a memory leak, and we all remember that from C, and we're allocating stuff off the C heap, so it's not surprising that the evils of C are revisited upon us. And so to try to make that safer and make it harder to make that mistake, where we can engage try with resources, if we make these things auto-closable, it's easy to program in a way where it's likely to be disposed of reliably. This is one of those, you get more power, but with power comes responsibility. If you forget to close the segment, then you've got a leak. Okay, so let's put these examples together and show what it looks like to read and write the little array of structs we had. So we've got a memory segment. We say, okay, we're going to allocate a memory segment called points, and we're going to say, give me a native segment, and how big is it? Well, it has to hold space for 5 points. A point is 2 ints, an int is 4 bytes, so we do some explicit multiplication and say, give us a segment that's 40 bytes wide. And so it allocates a segment for us, and that's great. And then we say, okay, give us the base address, which is going to point at that first point. And now we want to write into each of these XY values, and we're going to do this in a loop. Okay, so we have the var handle code that I showed you a few slides ago. It's exactly the same. We say, get me a base var handle for reading and writing ints. And if we want to read the X values, they're going to be every 8 bytes starting at offset 0. So we say take that int var handle and we associate a stride of 8 with it, and that will read us the first X value, the second X value, etc., according to the index that we pass it. And then we do the same thing for the Ys that are just offset by 4 bytes. And then in our loop, we say start at the base and set, we call the set on the var handle, which is going to write into memory, and we're giving it the base of the segment, the memory address, the index, which is our loop index, and the value to write. And so we're going to write I into the ith element of the array. So we write 0 into the first element, 1 into the next element, 2 into the next element, etc. and then we do the same with the y values. Okay, so this is it's pretty low level, right? You're dealing, the var handle API is intended to compile down to direct memory access instructions, so it's pretty low level, but it's handling at least some of the of the addressing computation for you. And so that's a good start, but I think we'd like to do a little bit better, because if you look at this code, you see it's full of magic constants. And magic constants are a bit of a smell. If you're calculating your own addressing and indexing, that's something that's easy to get wrong. And so we'd like to do a little bit better. But the code, the structure of the code is fairly straightforward, right? You say, give me a segment, start at the beginning, loop through them, write the corresponding x, write the corresponding y, go on to the next element. And so, if we can clean up the constants, I think it'll look pretty good. Okay, so let's talk about memory layouts, which is our approach for cleaning up those constants. So the goal of this piece of it is we want to make the code less brittle, less subject to small errors, and especially make it easier to change the behavior of the code if we want to change our layout without having to manually recompute all of those hardwired constants. And big surprise, how are we going to do this? Well, we're going to do this via a symbolic description of the layout of our struct. And so we need something that captures element sizes, types, alignment constraints, repetition, etc. And then we should be able to derive all of these offsets and strides and all of that directly from them. Okay, so I'll build up an example from the inside out. We're trying to describe something that is an array of 5 structs, where the struct has an int and 2 ints, x and y. So I'm going to create a thing called memory layout, which describes a struct. And the outermost thing is I'm repeating something 5 times. So I'm going to say, give me a sequence layout, and here's the repetition count. And now I have to provide something else. I have to provide a description of what it is I'm repeating. And how am I going to do that? Well, I'm going to do that with a layout, of course. So I'm going to say the thing that I'm repeating is a struct layout. And now I have to say what's in the struct layout. Well, it's going to have 2 actual values. I say, give me a layout for a 32-bit int, and give me another layout for a 32-bit int. Those are going to be the layouts that describe x and y. And I'm going to give them names. And the reason I'm going to give them names is I'm going to want to be able to say, give me a way of accessing the x value in this struct. So, okay, so this describes a layout, which is repeat this 5 times. The thing being repeated is a struct. The struct has 2 densely packed 32-bit values, and they have names. Okay, so now if I want to say, if I want to refer to an individual x or y in that, I have to say which field do I want, x or y, and I have to give it an index. So I'm going to describe a mapping from this structure to one of those var handles that is correctly parameterized for what I want to do. So there's some rules for how to do this. You have to start with a compound layout, and then you have to describe a sequence of, give me this offset, give me this index, etc. And that path has to bottom out in a value layout, right? Here's the layout that I just put on the previous slide, and so I want to get a memory access var handle that describes all of the y values, that's parameterized by the base address of the segment and the index, and I'm going to have to give it a bunch of information. So I'm saying, take my layout and give me a var handle for it. The type of the var handle is going to be int, so I'm going to be accessing an int, reading or writing an int, and the first coordinate I'm going to pass you is going to be the index into an array. So the first element I'm diving into is a sequence. I'm going to have to give you an index into that. And then the next element that I want is a field of a struct, and I want the one whose name is y. And so this gives me a var handle that takes as its coordinates a memory address for the base and an index, and it reads or writes the corresponding y value. And if I put that back all together with the previous example that I gave, all of the constants go away, right? I say, here's my layout. It's a struct. It's an array of 5 structs. The structs have int x, int y, and now I call this the var handle factory. That gives me a var handle for all the x's, and I'm doing it by name, not by offset. And I have a var handle to give me all the y's, and I'm doing that by name rather than offset. And then the code at the bottom is pretty much the same as before, but I've derived all of my offsets and strides from the symbolic description. So this should be more readable, should be less brittle, should be less error prone. Now, this may seem complicated. It may seem like, boy, you're doing a lot of work just to read a byte out of an array. But this is working with mechanisms in the VM that the VM knows how to inline through very aggressively. So these var handles are all boiled down into constants that the VM knows how to scrutinize. And similarly, the memory layouts all boil down into constants. The memory addresses all boil down to constants. So we should get very good optimization out of the JIT. One of the problems we had in the ByteBuffer example was we were not getting good optimization out of the JIT because we had all this complex stateful mutable logic for managing all the pointers in the ByteBuffer and swapping them around and all of that. So the API has been designed here to be exceedingly JIT friendly, and it should compile very well. The cost of that is we have to do a little bit more work up front. But once we do all that work up front of defining our layouts and our var handles, it's actually pretty easy to use. So let's talk about safety, and then I'll talk about performance. We want this to be a safe API. Safety means different things in different situations. So in this situation, what we mean is you shouldn't be able to read or write to an unmapped location and cause a seg fault. You shouldn't be able to write outside the bounds of the buffer that you're working with. Those should be turned, rather than being seg faults, they should be turned into user errors or exceptions. So we have to worry about out-of-bounds access, and we have to worry about access to memory that's already been freed. And this API gives us both of those, fairly effectively. And the key in building an API like this is you want to bake the safety in, but you want to bake it in a way that the JIT can optimize away, right? So bounds checking in Java is very fast. Array access in Java is fast, even though it's doing a bounds check on every access, because it's not doing a bounds check on every access. The compiler looks at your code and says, I can, here you have a loop from 1 to n. I don't need to bounds check on every array access. I can hoist that check outside of the loop and say at the beginning, is the array bigger than n? Great, okay, let's blaze through. Right? So we want to get the same kind of optimization out of this array, out of this API that we do with ordinary arrays, where the JIT can hoist all the checks out, and we get all the benefits of safety without paying for it in performance. So if I say, okay, give me a var handle for for an int and a memory segment that's that's, let's say, 10 bytes long, and I try to read that int at an offset of 42. That's 10 ints long, so it's 40 bytes wide. If I try to read out of offset 42, I get a nice clean exception, illegal state exception, out-of-bound access on segment. And it tells you, here's the thing you were trying to read at, and here's how big the buffer is. Similarly, if I go ahead and close the segment, and then I try to read or write from it, I get a similar exception, this time over temporal bounds, saying, sorry, you tried to access the segment after it got closed. Out of luck. Nice clean exception, no crash. So let's see how it performs. So here's these are the numbers from the previous chart where we said, okay, here's the unsafe value and the best that we got with ByteBuffers. Let's see how it works with the memory access API. Okay, well, this was our first try, right? This was the, like, you put it all together and plug it in and, the lights don't come on the Christmas tree kind of experience. So we needed some digging. We did some digging to find out what was happening. And we looked at the structure of the code. We said, okay, we're calling this offset method all the time. Is this confusing the compiler? Is it, is this getting in the way of certain optimizations, et cetera? So, we sort of dug at the cause of it for a while, and we tried a couple of things. We ran it with a different JIT compiler. We ran it with the Graal compiler, which has great escape analysis. And we saw, okay, we got a much better looking number out of it. So that kind of suggests that there was something that was interfering with C2 escape analysis that was giving us that terrible 33.8 performance number. So we called up the JIT guys, and they went and beat on the compiler with a tire iron for a bit, and found a couple bugs and found a couple places where we weren't hoisting things that could have been hoisted, and with a relatively small patch, we got this up to a throughput of 150. Which shows you a couple things. It shows you just how important it is that the compiler is able to hoist away things like bounds checks for you. And there are all of these strange accidental things that can get in the way, and the more complex and stateful your API is, the more likely one of those things is going to get in the way of getting the performance you want. So this was an API that was designed from the ground up to be JIT friendly. In the first round, the JIT didn't quite get the message, but we hit it hard enough, and it had the appropriate attitude adjustment, and everything was good. So this is a little bit of a story of of how the sausage is made, right? There are a number of things that can confuse the JIT, that can cause it to not recognize that an allocation can be eliminated with escape analysis. There are certain code paths where you combine certain idioms where you combine a hot path with a cold path, and it confuses the JIT's translation. That we found that happened with wrapping things with try with resources, where the outside path was cold but the inside path was hot, and that got in the way. There were also some interactions with the memory barriers that had to be worked out. And it turns out that where C2 is better at range check elimination on int index, but not on long index. So there's some more work required to be done there. But with a little bit of JIT work, we got the numbers that were kind of what we were expecting. So that's a pretty good outcome. Let's say you've got an application built around ByteBuffers, and you've seen this stuff, and you say, hey, I want to use that. That seems really cool. But all of my code is designed to work with ByteBuffers. Well, not a problem. There's a bidirectional conversion between a memory segment and a byte buffer. You can take a byte buffer and wrap it with a memory segment description. You can take a memory segment and wrap it with a byte buffer description. And this works, and there's a few mismatches that get in the way. So, for example, memory segments are deallocated explicitly with close, whereas byte buffers are disposed when the garbage collector decides that they're not reachable. And so this means that when you're wrapping one with the other, you're kind of exposing yourself to both of these programming models. And so, we do some work to make sure that when you wrap one in the other, it's at least as safe as, the safer of the two. So if I take a memory segment and I wrap it with a byte buffer, and then I close the underlying segment and I try to access through the byte buffer, yay, I get the appropriate error message, which means that I'm getting all the safety I get from the memory segment API plus the behavior of the byte buffer API. So this is in pretty good shape. There's a couple of things to work on in the future. One of the things that we want to work on in the future is concurrent access. All the examples so far have been one thread managing one buffer, so I haven't had to worry about synchronization. If I want to share a buffer between threads, well, that's harder. I have to deal with race conditions, although leaning on var handles there was a really good move because var handles provide all kind of fenced access to memory where you can say, I want the effect of a volatile reader or a write, I want the effects of a plain read or write through the same abstraction. So that part is pretty good. There's also another kind of race condition when you're sharing these things with multiple threads, which is one guy closes it and the other guy wants to use it. And now you have a race between the guy closing it and the guy trying to use it. So that one is a little bit harder to work out, but we have a story for that. So if you want to use these things in a concurrent environment, you can. They're just a little bit more complicated to set up. They start off in a confined state where they're owned by one thread, and then you can share. You can transfer the ownership across threads, or you can say derive from this confined buffer, a shared buffer, and then there's a protocol for figuring out when all of the accessors are no longer using it. I don't want to dive into details. There's a paper at this at this URL about it. So okay, let me sum up, and then we'll have about 5 minutes left for questions. Basic point of this API is to have a low-level building block for off-heap apps, so that we can get people. I think people will give up ByteBuffers fairly readily because they're hard to use. Hopefully, we can migrate some of them off of Unsafe because it is safe and it is efficient. You get spatial checks, you get temporal checks, you have a robust ownership model in the concurrent world, and the JIT is very good at eliminating the bounds checks and the ownership checks, and you get deterministic deallocation, which you didn't get with ByteBuffers. So if you're interested in checking this out, you can go check the code out. There's already JavaDoc up there. This is something, like I said, we're in the process of putting in as an incubating module, either in Java 14 or 15. Not clear when it's going to land, but we'll find out fairly soon. And if you're doing this sort of stuff, we would love to hear your feedback. So with that, I have about 4 minutes left for questions. So I may not be able to answer the questions because it's not work that I've done, but I'll try. Sir.
If I correctly understood, only one way to prevent memory leak is to properly close memory segment. The question is, what prevents you from adding a backstop for garbage collection? Is it done for that?
Yeah. So the question is, okay, it's on you to close it, and if you forget to close, you have a memory leak. Could you also engage garbage collection using something like cleaners or something like that to deallocate it for you if you forget to close it? Probably. I think that would probably be more confusing. It's not that hard to dispose it when you need it because these things are auto-closable. You can wrap the whole thing in a try with resources, and then when you're done using it, it gets disposed deterministically. So I don't think that's a big problem. But if it is a big problem, we could certainly look. If you were to wrap one of these things in a byte buffer, you would effectively get that behavior. But then you would have to make sure that the byte buffer goes out of scope at the same time the segment goes out of scope. So you could do that if you wanted to. But I don't think we need to build that directly into this API. Question?
Will you remove all the access to unsafe and ByteBuffer in the JVM with this thing?
So the question is, will we remove ByteBuffer and unsafe after this works? So
usage of it in the JVM yet?
In the JDK libraries, in our own libraries. So there's nothing wrong with ByteBuffer. ByteBuffer is great for non-blocking I/O. So we will probably continue to use that because it isn't broken. In terms of using unsafe inside the JDK, if there is a better alternative, we may do that. We may continue to use unsafe because the considerations inside the JDK are different from considerations in libraries outside the JDK. So there will probably be some degree of reequilibration, but I don't imagine a program of getting rid of all of it necessarily just for the sake of it. There was a question here, and then there's a question in the corner.
I was thinking about alignment. When you laid out the front, you said 32-bit fields or whatever. Does it handle alt alignment access?
Yeah, so the question is, what about alignment? And secondarily, what about padding? And secondarily, what about big endian, little endian? Yes, and bit fields and all of that. And the answer is yes to all of that, right? So, this was a simple example of packing two ints in, but there are layouts for padding. There are layouts for alignment. You can attach ordering to fields, all of that. So if you have a more complicated layout, you can describe it that way. Question, probably the last question.
My question is related. So what if there's no direct match of the data types? Just to define the layout in terms of bits?
So the question is, what if I don't have, what if my data type isn't an int, a long, a char, a byte, or one of those things? Yes, you can describe a number of bits, and then you have to deal with it on your own. So with what's going to happen there with var handles don't deal directly with bit fields; they deal with a carrier. So if you if you have a field that's say 17 bits, you're going to have to use an int as a carrier and maybe do some masking to get rid of that.
But the casting is done automatically.
I'm not sure if the masking is done automatically in that case with the var handles. I think it probably is not. So, all right, I think time's up. So thank you very much.